In this video, we're going to talk about elements, compounds, and mixtures. Elements and compounds are going to be on this page. Mixtures will be on the back. So let's start by comparing elements and compounds. Now, one of the important things that we learn in the very beginning of the year is we learn our elements on the periodic table, specifically the first 40 elements. They're all important, but the first 40 are the ones that we tend to work with, so they're good to know. And one of the reasons we want to know them is distinguishing between elements and compounds. Elements are found on the periodic table. Compounds are combinations, that's the root of the word, of two different elements found on the periodic table. It can be more, but it's got to be at least two, obviously. So if you have two or more different things put together from the periodic table, it's called a compound. If you only have one thing from the periodic table, now it doesn't matter if you have one atom of the same element or two atoms or three atoms or more. If they're the same element, then they are considered an element. So elements can't be broken down into something different. That's the key, into something different, whereas compounds can be separated. So if you have two or more different elements combined, you can separate them out and you get their individual elements back. So that's some of the main differences. Now we have two words that are very important. The words are atom and molecule. They are basically the same thing. Okay, the only difference is when we call something an atom, we say it's the smallest whole unit that retains all of the properties of the element. So a single atom of gold, if you could see it, obviously it's too small, but if you could see it with your eyes, it would look just like any ordinary piece of gold. It would be the same color, the same shine, it would conduct electricity the same, it would have all the same properties except size and mass and volume, because those obviously do change with size. So that's an atom. Now a molecule is basically the same thing, but it's uniquely for a compound. So if we talk about a single molecule, we're talking about the smallest unit of a compound that retains the properties of that substance, whereas atom is the smallest unit of an element that retains all the properties. So they're basically the same thing. Molecules or compounds have what we call a definite ratio. In other words, you cannot change the ratio without changing what it is. And that's very important. In other words, we all know that water is H2O. But if I were to change the ratio of H's to O's, I will change the compound itself. H1O would be a base, H3O would be an acid, and if I went to H2O2, that's hydrogen peroxide. So just by changing the ratio of H's and O's, we change the identity of the compound to a different compound. There are some, and then compounds by definition are binary, and that means that they are made from two or more different elements, not necessarily two atoms. In other words, they're all going to be at least two or more atoms, but the atoms have to be, at least two of them have to be different elements in order to be a compound. Okay, so just be aware of that. Now, the last bit for elements is that there are some naturally diatomic elements. This is a fake word. I call it Brinckelhoff, if you were to read it out, Brinclhof. These are the 7 elements on the periodic table that are naturally diatomic. Unfortunately, they are not listed on the periodic table as being diatomic. You will have to know that they are naturally diatomic, so unfortunately, you do have to memorize the word Brinckelhoff. Let's go into how we would draw these. So if we look at some of these diagrams, these circles represent atoms, and so elements can be drawn this way. Single atom, doubles, or triples. If you notice, they're all the same color. I made these white. They could be black, green, purple. It doesn't make a difference as long as they're the same color. So in other words, single one, the color doesn't matter. It's irrelevant because it's only one atom. Doubles and triples, they all have to be the same color. Okay, and that would be an example. An example would be a single oxygen atom, O, a diatomic oxygen, which is the oxygen that we breathe, O2, that would be like that. And then there's triatomic oxygen, which is what's in the ozone layer. We call it ozone, O3. It would kind of look like that. And so these are all considered elements because since let's say that they're all oxygen, for example, if I break them up, I still get the element oxygen. I'm just going to not have two. Instead of two, I'll have one. And instead of three, I would have singles or doubles or whatever. So they're all the same because you don't get different things when you break them up. Compounds, if you notice, the size, the shape, the color, doesn't really matter. Okay, the only thing that really matters is the smallest possible compound would be this atom right here. It's got two different colors, okay? And then the colors represent the elements themselves. So this could be one element, that's a different element. You could have two of the same as long as one's different. You could reverse it. They could have an angle to it. We'll get into that more. There could be 4 elements. There could be 5 elements. There could be 1,000,000 elements. It doesn't make a difference as long as one of them just one, happens to be a different element than the rest of them, you've got a compound. So these are all examples of compounds. If you notice that some of the things that they all have in common is that no matter how many atoms they have at least one that is a different element or different color than them. Whereas with the elements, they're all the same color or they're all the same element no matter what. So that's the real easy way to distinguish between them. So now we'll talk about mixtures. Mixtures, there's two types, okay? So a mixture is a combination of two or more different substances. I use the word substance because that could be an element, it could be a compound, it could be any combination of the two. So it could be two different elements, two different compounds, it could be an element, a compound. It doesn't make a difference, okay? And it could be obviously way more than two. Each substance retains its own identity and properties. An example, salt water. All right, so if I drink salt water, it's going to taste like water and it's going to taste like salt. If I mix sugar and salt together and I were to eat that, it would taste like salt and sugar. I wouldn't get something different. It's not like if I mix sugar and salt together, I all of a sudden get bubble gum. It doesn't work like that in terms of flavors. You would expect to taste the two individual flavors. Now, they have variable ratios. What that means is that you can have salt water with a little bit of salt and you can have salt water that's super salty. That's variable. The reason I mention it here is because it is different from a compound. If you remember from the previous page, compounds have definite ratios. You cannot change the amount of each element without changing the identity of the compound. In a mixture, you can. The reason I'm mentioning this is because a lot of times multiple choice questions will try to get you to confuse those two, which one's variable and which one's definite. Obviously, elements, there's no ratio because they're all the same thing, so it's 100% of one element and that's it. Doesn't matter how many there are. That's why we don't really talk about them in that way. Now, mixtures, the two types that I mentioned, there's heterogeneous and there's homogeneous. Now, you've heard the word genus before in biology. You've probably hopefully remembered that. Kingdom, phylum, class, order, family, genus, species, right? So the genus is the type, and homo and hetero we've definitely heard obviously in biology, but in terms of chemistry, the words are Latin and they really just mean same and different. So heterogeneous literally means different types, and homogeneous means same types or uniform types. And what that's referencing is what you see. In these mixtures, in a heterogeneous mixture, there's going to be a visible difference that you can see with your eyes that's obvious. In a homogeneous mixture, there's going to be no visible difference. You're not going to be able to see the different things. That's why they're called the same type versus different types. So an example, if I mix salt and pepper together, I can see visibly that the salt is the white stuff and the peppers would be the red or the black, or the white, well, depending on whatever pepper you use, but that doesn't really matter. So I'll see different things. Sand and water, I would see the sand usually at the bottom and then the water would be everywhere else. Salad, when we think of salad as the most basic lettuce and tomatoes. I'll see lettuce, I'll see tomatoes, they're different things. Dirt, now this one throws people off because unless you've actually gotten into dirt and or you like to garden and things like that, you may not have noticed from a distance, dirt just looks like dirt, okay? But when you get up close, you see that dirt is made up of lots of different things. It's got sticks and sand and bugs and leaves and poop and all these different things in the dirt that makes it a heterogeneous mixture, but it's a little bit harder to see if you're not actually looking very carefully at it, okay? Whereas with homogeneous mixtures, these are things that all just look the same. For example, air. You wouldn't think of air as a mixture, but it is in fact a mixture. We never said that mixtures had to be pure liquids. They could be combinations of different things. So for example, air is a mixture because if we know that there's at least two things in air, right? We breathe in O2, we breathe out CO2. So granted, that's two different things. So therefore air is a mixture of the combination of the two things. And I can't see where the CO2 and the O2 are. It's not like, I walk in a room and I'd be like, oh, wow, the oxygen's really good over there. Let me go breathe in that corner of the room. It doesn't work like that. It's all evenly distributed. And even if it wasn't, I couldn't see it anyway. Alcohol and water. So that would be basically like vodka. Vodka is a homogeneous mixture because you can't see where the alcohol and the water are. They're all mixed evenly. Unlike oil and water or salad dressing where you can actually see one versus the other. You don't even need to know which one's which. You just need to know that they're different. Salt plus water is a homogeneous mixture as well. Took me a second there. Salt water is a homogeneous mixture. So now the thing about salt water, and this is why I paused, and we have to be a little bit careful here, is we are talking about salt water that is fully dissolved. So not if you, when you initially like put salt in water, you will see the salt at the bottom of the container. That doesn't count. What we're going to do is we are going to wait for all of that salt to fully dissolve, and then we would determine if it was homo or heterogeneous. And once it's fully dissolved, if I had a glass of salt water in front of you and a glass of regular water in front of you and a glass of alcohol and water in front of you, without smelling or tasting, you would not be able to visibly tell the difference between them, assuming the salt was clear. Obviously, some salts have color to them, but we'll get into that later. So that is what we would call an aqueous compound, or something that is dissolved in water. So for example, sugar water looks like that. C6H12O6 is the most simple sugar we have. We call that glucose. We should know that already, but it doesn't really matter. The AQ just means it's dissolved in water. So if I had a glass of sugar water, it would, chemically, I would write it out like that. Okay, so now a common question a lot of people have, or problem, is determining between a mixture and a pure substance. And it's pretty simple. If you can't name the things that make it a mixture, so if it's not a mixture of A and B, or what, thing one and thing two, however you want to say it, if it's not a mixture of these two things or more, then it's going to be a pure substance. And when we go over some of the practice problems, I will explain the differences and go over a bunch more examples. But basically, you have to be able to name some of the things that is in the mixture for it to be a mixture. If you can't name the different things, then it's probably not a mixture. Like, for example, salt water. I could say, well, there's salt and water. That's two different things. That makes it a mixture. If I was talking about just water, well, it's water. There's no second compound there to name. Now, or there's no second element there to name. There's no second anything besides the H2O, which is its own compound. That makes it a pure substance. So hopefully that explains the differences. We'll go over some more practice problems in the next video. Hopefully that will clear any confusion up.